Now let's look at the bottom of page 67, and we'll stop at the bottom of page 72. So the second law of thermodynamics is now going to be defined. Entropy is the physical quantity that is linked to the number of possible ways in which a particular state can occur. Entropy is used as a predictor of spontaneity because the most probable state of the system is the one with the largest number of possible arrangements. The second law of thermodynamics says all processes, all spontaneous processes, must increase the entropy of the universe. And so the universe as a whole must become more disordered. So for all spontaneous processes, the following are true: that the entropy of the universe is going to be greater than 0, which means that the entropy of the system combined with the entropy of the surroundings should give you a positive value for the entropy of the universe. So the entropy of your system and your surroundings cannot be equal to one another because you have to have an overall positive value. So let's kind of break that down a little bit. So imagine a phase change like melting or dissolving a solid into a liquid, or even a chemical reaction. Those would be considered the system. And then everything outside of those would be considered the surroundings. So ice melting, the ice would be the system, and then if it's just sitting on the countertop melting, then maybe the air and the table would be the surroundings. Or if it were in a glass of water, then the ice is the system and the water is the surroundings. Same thing with something like dissolving. If you put some salt in water, then the salt is going to be the system and the water is going to be the surroundings. Of course, over time, the salt water together becomes the system. So when you talk about both of these two things in comparison and together, then they both make up the entropy of the universe, or the total entropy. When you consider both of these together, you're focusing on the total entropy. Note here at the bottom that the delta S, or the entropy of the system, is a state function, while the entropy of the universe and entropy of surroundings are not state functions. So what you should understand based on the above information is this: that if you have a reaction that's spontaneous in the forward direction, then its delta S total, or delta S of the universe, is a positive value or greater than 0. So the delta S for the universe is positive, or we can assign it like this. Keep in mind that delta S universe is the same thing as delta S total. If the delta S is a negative value, then that means the reverse process is going to be spontaneous, so the reverse reaction. Or if your delta S total is a negative number. Now let's look at a reversible process, or a system that is at equilibrium. Keep in mind that any phase change is an example of a system at equilibrium, like during the process of melting or freezing or boiling or condensation, etc. So the delta S of the universe is going to equal 0 when you're in a state of equilibrium. That means that there's a perfect balance of entropy in the system and entropy of the surroundings. And so they should be equal to one another, where the delta S of the system is equal to the negative delta S of the surroundings. So here would be our little note card for when you have a system at equilibrium. The delta S of the universe is equal to 0, and that is at during any process that is in equilibrium, which means the delta S of the system is equal to the negative delta S of the surroundings. Or when you combine the two, they should equal 0. Note that delta S without a subscript automatically implies it's the delta S of the system. And so here's a note card for that. If you see delta S, we're going to automatically go with that must be the delta S of the system. The direction of spontaneity is determined by the change in the quality of energy. If you have a spontaneous process, energy will always become dispersed in a more disordered way. Or if you have a spontaneous process, the entropy of the universe is going to be positive. There will be more entropy, or a higher entropy, or more disorder. This is a consequence of the fact that the universe is made up of a very large number of molecules and they function independently. So clarification: if A to B is spontaneous, then the reverse process is not spontaneous. If A to B is reversible, then B to A is also reversible. Entropy changes for the system. The process in the system determines the delta S of the system. When the delta S of the system is greater than 0, disorder must be increasing in the system. What this means is when there is a delta S of the system less than 0 or negative in value, then the system becomes more orderly, less disorganized. The delta S system is less than 0 for the following reaction because 2 molecules have more order than 3. So if we look here, we have 2 plus 1 is 3 moles of gas before the reaction, and then only 2 moles of gas after the reaction. And so the greater the amount of moles in gas, the higher the entropy is. So the reactant side has more entropy and the product side has less. And so the system's entropy has decreased. Notice that the heat was ignored. Only the process in the system was considered. The heat leaving the system comes from the breaking and remaking of chemical bonds. The temperature of the system is not changing. Here's another example. The delta S system is greater than 0 for this reaction because a tremendous amount of disorder is created when materials dissolve into solution. So before we have a solid, but when you place the solid salt in water, then the ions break apart and they start spreading and they become aqueous. So this scenario is more disorderly than the original. So here's where it's a solid, and then as it dissolves, you can see how the particles become more spread out, and so this is considered more disorder. So this system has a higher entropy than it did beforehand. Another example. When the system is heated, delta S of the system is greater than 0 because more disorder is created. So if we look here, here's where it's cooler and it's in a solid form. And then as you heat it, it melts and the particles begin to spread apart from one another and move faster. And so this is a scenario where the entropy has become greater. It's more disorderly, and so this has a positive delta S of the system. Similarly, when an object is cooled, the delta S is negative because more order is created. When volume increases, the delta S of the system becomes greater than 0 because more disorder is created. There are more ways that the molecules can be arranged in the larger volume. And so if you'll look here, because there's less space, the particles are more orderly. However, when you have more space, then the particles can spread out and then they become more disorganized or disorderly. And so this has a greater entropy than this does. Anytime you have a phase change, as you move up from solid to liquid to gas, the entropy becomes more and more. You have a greater value of entropy. So if you look at this diagram here, as you move from solid to liquid to gas, there's a greater entropy. But if you go in reverse, gas to liquid to solid, then it becomes more ordered or organized, and so the entropy becomes less and less. So let's look at example 19.20. Determine the sign of the delta S of the system for these processes. Number 1, notice that we have 3 plus 1 makes 4 moles of gas on the left, and we go to 2 moles of gas on the right. We have 4 moles of gas, and we're going to yield 2 moles of gas. So we have more order as products, and so the entropy becomes less. And so we'll say this has a negative delta S. The delta S is getting less and less. Okay, let's look at number 2. In number 2, it's a little more challenging. On the left side, you're dealing with a solid and liquids, and on the product side, you have a solid and gas. We really only care about the change in gas because that's the only thing that has a very significant difference from before and after. So here I would say I have 0 moles of gas to begin with, and then I have 1 mole of gas afterwards. And so I would say this has a positive increase in entropy. There's more disorder afterwards. Again, solids and liquids are pretty similar as far as the amount of space that they take up, but gases take up a very large amount of space, and so it's much more dramatic, and so we can just focus on gases. All right, number 3. In this case, we don't have any gases, so we have to look at the fact that we have 2 plus 1 is 3 moles of aqueous solution, and then notice as our products we have 2 moles of aqueous, and then we have a precipitate. And so keeping in mind that this means that beforehand I had sodium and chloride ions and lead ions and nitrate ions all in the system, but then afterwards all I had were sodium ions, nitrate ions, and a solid precipitate of PbCl2. And so it's become more organized afterwards, and so I would say this has a negative delta S of the system.